In recent lectures, we've been addressing the use of Newton's second law for starting with motion observations and then solving for unknown interactions. We've outlined a series of key steps to help us with this. Most recently, we've discussed at length how to think about changes in velocity and changes in momentum along a direction parallel to the system's motion and perpendicular to the system's motion. Moreover, we've used a bit of calculus to decompose the change in momentum over the change in time into separate parts along each of these directions. Now, as we have said, all of these quantities can be obtained by focusing just on the system. They're quantities we get from just watching the motion or from properties of the system itself. Today we'll discuss how all this links to the very different physical quantities coming from the surroundings, the total interactions, the net force of the surroundings acting on the system. It's probably no surprise to you that Newton's second law is, of course, the foundation of this linkage. However, you may be surprised to discover here how much we can actually say about the net force without even knowing any specifics about what agents and what interactions in the surroundings are contributing to Fnet. Let's start with our fundamental principle, emphasizing here the cause and effect meaning of this. When we observe velocity changes or momentum changes in our system as we watch it for some period of time, Newton's second law tells us that non-zero total interactions in the surroundings, which is to say a non-zero net force on the system, are the causes and the motion changes are the corresponding effects. In the same way, if we observe no effect in the sense of no changes in velocity or no changes in momentum, then there is no cause in the sense that the net force is zero. Now let's not fall into the trap of thinking that no net force means no forces at all. There may or may not be interactions. All Newton's second law tells us here is that if there are interactions, they must all add to zero if there are no changes in velocity or changes in momentum. Now, our decomposition of motion changes along parallel and perpendicular directions allows us to use Newton's second law to make even stronger cause and effect statements. So when we describe motion changes using delta P over delta T expressed in terms of the two main parts, delta P over delta T parallel and delta P over delta T perpendicular, we're describing effects that must have corresponding causes, namely two separate parts of the net force, which we'll call Fnet parallel and Fnet perpendicular. This means we can make two independent, distinct cause and effect statements here. First, if the object is speeding up or slowing down, then as we discussed, we know that delta P over delta T parallel is non-zero and points along the direction of the object's motion, either in the direction for speeding up or opposite to this direction for slowing down. All this describes an effect. Newton's second law tells us there must be a cause, a non-zero Fnet pointing in the same direction as delta P over delta T parallel to cause this. If there is no speeding up or slowing down, no effect along the parallel direction, then there is no cause. Fnet parallel must be zero. Second, if we see the trajectory, the path of the particle's motion is curving, then we know that delta P over delta T perpendicular is non-zero and points toward the center of the kissing circle. Again, this describes an effect. Newton's second law tells us that there must be a cause, a non-zero Fnet perpendicular pointing toward the center of the kissing circle, the same direction as delta P over delta T perpendicular, to cause this. If there is no curving of the path, there is no effect along the perpendicular direction, and therefore there is no cause. Fnet perpendicular must be zero. Let's look at some specific examples. Let's say our system moves in a path like this, a straight line, and we observe that it is speeding up. What is the direction of Fnet? To find this, we'll always start with describing the effects, the changes in motion. First, for a trajectory like this, speeding up means the system momentum later in time must have a larger magnitude than the momentum earlier in time. The change in the magnitude must be positive. When we divide this by delta t, then we still have a positive scalar that, when we multiply by p hat, we then get the vector delta p over delta t parallel pointing in the direction of the motion. This is the effect we observe. Then, by Newton's second law, this effect must be equal to the cause, a total force along the parallel direction that must also point in the same direction, the direction of the object's motion. Even more strongly, if we calculate quantitatively d magnitude of p dt, then by Newton's second law, that quantity tells us what the magnitude of Fnet parallel must be. And therefore, we can learn everything about Fnet parallel without knowing specifically what agents in the surroundings are responsible for Fnet parallel. Next, let's look at the curviness of the system's path. It's not curvy. We see no curvy effects, which suggests that delta p over delta t perpendicular is 0. This may seem a bit mysterious if we look at the expression for the magnitude of delta p over delta t perpendicular. We see that magnitude is the magnitude of p times the magnitude of v divided by r. And given that the system is moving, we know that the magnitude of the velocity and the magnitude of the momentum in the numerator must both be non-zero. But what about the kissing circle radius? What is that here? Now, recall earlier we said that a small r corresponds to a sharply curving path, like this. The more gentle the curve, the larger the radius of the kissing circle. It's clear that a path with only a very slight curve will have a very large r. In fact, in the limit that r goes to infinity, a very slight curve goes over to a straight path. So, with r in effect infinite here, delta p over delta t perpendicular is 0, meaning no curvy effect. So, by Newton's second law, we should expect no cause, meaning Fnet perpendicular must be equal to 0. So, since these two parts, Fnet parallel and Fnet perpendicular, must add up to give Fnet, then, since Fnet perpendicular is 0, we conclude Fnet is equal to Fnet parallel, and therefore Fnet must point in the direction of the object's motion in this particular case. Let's take this same path, same trajectory, but make one change. Let's say the system is slowing down. What would the direction of Fnet be in this case? Give this question a try. To find the correct answer here, we can do that by following the same reasoning as before, starting with looking at the effects. Since the particle's path is straight, no curviness, then we know delta p over delta t perpendicular is 0 for the reasons we just discussed, and therefore, by Newton's second law, Fnet perpendicular is 0. For the parallel direction, if you follow the same steps we outlined earlier in the lecture, delta magnitude of p over delta t is negative, so that delta p over delta t parallel points opposite to the direction the object is moving. And therefore, by Newton's second law, so must Fnet parallel. And since Fnet perpendicular is 0, Fnet is equal to Fnet parallel, and so must also point opposite to the direction of motion in this particular case. Let's now tackle a case with curviness. Here's a particle moving at constant speed in the circular path of radius r. At the instant where the particle is located as shown, what's the direction of Fnet? First, we observe that the particle is neither speeding up nor slowing down. So that means delta p over delta t parallel is 0. And so, by Newton's second law, Fnet parallel is 0. Next, because we see curviness to the path, we expect delta p over delta t perpendicular is non-zero. To find this, we need to describe the kissing circle that fits the path. Here, that's easy because the kissing circle is just the particle's path itself. That means the direction of delta p over delta t perpendicular is, as always, toward the center of the kissing circle, so that, by Newton's second law, the cause of the curviness, Fnet perpendicular, must also point in this same direction. Now, since Fnet parallel is 0, then Fnet must also be equal to Fnet perpendicular. Therefore, Fnet must point toward the center of the kissing circle as shown. If we know the system's speed and momentum, then we could go further in this case and determine the magnitude of Fnet. Since we're told that the radius of the circle is r, then if we know the magnitude of p and the magnitude of v, then the magnitude of delta p over delta t perpendicular must be magnitude of p times the magnitude of v divided by r, and by Newton's second law, this must also be the magnitude of Fnet perpendicular. Finally, since Fnet equals Fnet perpendicular in this specific case, the magnitude of Fnet must also be the same. A couple of final notes here. The quantity speed squared divided by r is sometimes called the centripetal acceleration, where centripetal just means pointing toward the center of the kissing circle. Now there's no new physics here, just new vocabulary. The centripetal acceleration is just another way to label the trajectory curviness effect that we observe. Along these same lines, here's more vocabulary and a cautionary note. The system mass times the speed squared divided by r is sometimes called the centripetal force. This is unfortunate language, as this quantity is not a force. It's just another confusing name for delta p over delta t perpendicular. The centripetal force describes the effects here, which Newton's second law tells us is caused by some non-zero Fnet perpendicular acting in this case. Notice in all of our discussion today, all of our understanding about Fnet in all of these cases came through watching the system move and applying Newton's second law. We can learn specifics about Fnet in these cases without even knowing what agents in the surroundings were acting on the system, and even without knowing anything about the system itself except its mass. Of course, if we know more specifics, like if we can identify the agents and corresponding interactions, then we can solve for the direction and magnitude of one or more of those specific interactions. We'll do some examples like this in our next lecture.